Welcome back everyone, and we're back with one more video about raycasting, and this time we're going to do a biggie. This one's going to be about terrains. We've done all the basic shapes we've up till now, and now we have to deal with something more complicated, which is a terrain. It's not a shape. A terrain can be any number of things. If you do a search, you'll see like a lot of good examples of what terrains are. You have mountainy areas. You can have something more spherical, like planetary, which I guess you can use spheres. Then you got non-convex shapes like this, which you need a different type of approach, because you have so many different types of intersections with I think a non-convex type of shape. So on and so forth. So like I said, depending on the terrain you're dealing with, different approaches. If you have like a flat terrain, then you could just use plane intersection. That's good enough. But like I said, with anything more complicated, you need to like a different approach. So like this is a picture of a pretty good example of an idea of an approach. The idea of this approach is kind of like a ray marching. You just keep going until you're kind of like inside the mountain, and then you kind of have your bounds. So that's kind of one approach that I guess this image kind of illustrates. The way we're going to go about it is an approach that Thin Matrix has in one of his videos. He just quickly kind of, it's like one of his videos is like kind of just a little bit about it, just a quick overview. And his idea works fairly well. It's kind of like it's a ray marching, but it's a binary search where you kind of, instead of just going through the ray from beginning to end, you kind of do a half, and then that half you decide. Then you pick a side, a half of the line, the top half or the bottom half, and then you cut that in half, and you just keep cutting the ray in half increments until you pretty much reach a point. That's perfectly intersects your array. So he has two videos. They're two separate videos, very far apart. One has to do with picking, which shows you how to calculate a point on a terrain, like a grid terrain, which I'm using, and another one about ray casting and how to do it on a terrain that's kind of bumpy. So definitely go check out his videos. He creates tutorials on how to build a game engine using Java and OpenGL. You get to learn quite a lot. Some things that he uses is not available in WebGL. There's a couple of cool videos that are just not possible because it's OpenGL version he's using. I don't know, it's 4 or 4.5. Has a lot more features than what OpenGL ES 3.0 has that we're stuck using with WebGL. So definitely give him a subscribe, and he has a Patreon. He definitely deserves it. He's also making a game, so definitely he's worth a look. Like I said, you can learn a lot from him. I do learn quite a bit watching his videos. So let's kind of get to it. So we're going to use the terrain object that we did, I think like 20 some odd videos ago. And by the way, this is episode 50. This is a great accomplishment. I've never thought I was going to get up to episode 50 with this series. I thought I'd probably quit by 10 or 15. So I'm very shocked that I'm actually got this far into this YouTube series. So we're this far out. We're going to use our old terrain, and I went back and I fixed it up. I made it into a JavaScript module, and I updated it where I can use this to create chunks of terrain. So this way, when this is just one piece, we can end up filling this whole grid area with chunks of terrain. So I'll show you a little bit of that later. So that's the first thing. We'll show you some of the changes to the code that are kind of important. One big change I did, like all the other previous videos we've been doing, I've been creating basically these prototypes. Like for example, I have the bounding box, bounding capsule, bounding sphere JS files, and those are the data structures for that type of bounding, and then the rendering of how to visually see it. I'm creating a new file called bounding volumes, and this is where I'm going to put all the the visual aspects of it, and the one that actually, the stuff that actually handles the definition of the bounding, I'm storing in something now called raycast.js. And here's a class AABB. So this is our bounding box definition, and this is a lot different than what we had previously. So if I go back to here, it has, you know, Vmax, bound, bound flat, draw. Everything's all mixed together, and you know, this is what our bounding box did look like when we were doing the tutorial. Like I said, this time around, I'm getting rid of all the prototypey stuff and building this the correct way. Because I always kept saying we're not building it the right way, we're just prototyping. So for this last video, really to recasting, I want to do this the right way, so that you guys kind of see how things are. So that's what I'm kind of saying. Bounding box is where our visualization is happening, and our old file ray is going to be discontinued, and it's going to be replaced by our file called raycast. So this is the definition of the bounding box. This is how all the data that represents it exists. Because the visualization stuff in here is really just for testing, so we can see the bounding box visually. Like this stuff at the end of the day is useless. We don't need this in our final application or final game, because we don't need to see the bounding box. All we care about is the bounding box information that defines it. Don't need that file. So this is our bounding definition for the bounding box, and this is the AABB. So like the last version, we're going to have a bounding array, but this time we're going to have two versions of it. We're going to have a local bounds and a world bounds, because our local definition and size is defined at origin, just like our object's going to be. But if our object moves through space, our object has a local position and a world position. So that's what this is all about. So our local bound is our default bounds related in relations to our object at origin that the bounding box is going to surround. And world bound is when the object moves, we're going to change these bound values based on the world position of the object that we're targeting. So I just have different constructors, kind of, basically. I can pass in one element, which I'm passing the target, and it calls the function set target. If I pass in two, I'm just passing in two vec3s. Those are my bounds. And if it's 6, I'm defining all the bounds with raw numbers. Most often, I'm going to be using this one. I'm just going to pass in the target, and that target I'll use the information from that target. So set target, I'm just going to save the reference to the object. Basically, this becomes like the child of the object. And if the bounds value exists, I make a copy of its bounds. Yeah, so that's about it. And then there's a function called update, which then takes our local bounds, adds the target's position, and updates it into world bounds. Like I said, this takes the information from our target and then moves our local bounds into world position. So this way, when we do calculations, everything's in world space. Like I said, everything kind of needs to exist in world space when we're doing a lot of our intersections. So that's our bounding box definition, the AAB. Then we have array definition. Before we had, I think it was just a simple object, like a struct that we created. This time it's going to be an actual object. And the actual object that has the values a little bit differently. So we have origin, because I think I started as start and end. Now we're going to use proper terminology. So this is the origin of array. This is the end of array. And at the same time, by taking these two values, we're going to know its vector length, because we need the vector length for a lot of calculations. And we need the same value but normalized, which is our direction. So it's our normalized direction, because in a lot of our code, we need those two values, and we end up calculating them in the algorithm. So when we have our array and we get our mouse information, we're going to calculate all the values that we need. So this way, when we do like a bounding box test, we don't need to calculate the vector length and the direction every single time. It saves us so that we do it once and then we use it all over the place. And for AABB, we have an extra function that we add an extra 2 sets of values for AAB testing, we're going to use Scratch a Pixel's algorithm because they have a nice optimized way of doing it. So their optimization is really just caching certain values in a certain way to kind of speed up the process, which is useful. So when I get the ray, I get back this ray object, and then if I'm doing bounding box definitions, I call this afterwards, so I can prepare 2 extra values. If I'm doing a bunch of spheres, there's no point of calculating this. I just want to save myself time. So if I know I'm doing bounding boxes, I'll do it. I'm just going to use it. I'm just going to call this when I get my array. And array also has 2 static functions. Is the mouse segment function is the same? Let me look at it. It's the same one. It's our point from mouse function. And our other one is direction from mouse, which I think I never defined it yet. So we're using our old direction from mouse, renamed it to mouse segment, because I want to start using terminology that's correct. A segment has a start and end position. Like a line is infinite, and then an array has an origin and array has an origin but an infinite direction. So there's math terms. So I'm trying to be smart about it when naming conventions. So when this function returned a segment, it gives you a start point and an end point. So that's, and the code's it's practically the same. It just at the end it creates the array object, fills in the data, and helps calculate the vector length and the normalized direction, and then kind of just saves it all in there for you. So our array cast is just an blank slate. It's these 2 functions that helps define our array information. So we have that as a static. The other one, mouse direction, I haven't implemented yet because I haven't used it. And I have a debug line, so I can pass in an array and automatically create a debug line for it so we can see it. And then inside it, we also have the AABB testing. So I pass in the box information, I pass in an array, and then you get 2 values actually. You get out, when you get the out value, you get our min and max t values, and you also get a true value. So when you do a test, you're gonna see. I'm just gonna test if it's true, then I use the out values. If I choose true false, and I don't care, because that means there's no values that were pushed out. So technically, you're getting 3 values from this function. And instead of returning position like we were doing in the previous, I'm just returning the t values, because most often, depending on what you're doing, sometimes you just want the t values and not position. So I'm better off just giving back the positions, and then in the application determine how I want to use it. Because when it comes to terrains, intersections, I don't need the position. I actually need the t values. So that's why I built it this way. And that is our array. And I have others other definitions I want to add in down the line. Because that's all the stuff we've done in the last, I don't know, we did like 6 or 5 or 7 videos about intersection. We did intersections about just about everything. So at some point down the line, I'll fill this in, or you guys can fill it in. Like I said, this is kind of like the starting point of the raycast mini framework. All the lessons we did. So everything that we've done so far, I'm just going to rebuild it into a mini library like this as I need it. So that is that. So that's our raycast. Don't need ray. Don't need bounding box and bounding box volumes. That's all the functions. All right. So we got our terrains. The terrains are basically the same thing. And it's ideally the exact same type of code that I did in the previous lesson. It's probably just fixed up a little bit more. It's a little bit more modernized. But it still creates a terrain, and it uses Perlin noise to generate the hills and valleys. And I have a new folder called extras. It's in the same level as fungi. So it's not part of fungi. I just call it extras. And this is where I'm probably just going to stick code I found online. And this one is Noise.js by Joseph PHG. I don't know. This is the same one that we used in the previous version. And I kind of added a little blurb here that I've done some changes so this is an ES6 module. So this entire thing I fixed up a little bit. I don't know how much. I don't remember how much I did. It's not too much. I just had to change a few things here and there. And at the very end, it returns a default module. So this way I can call it just like any other module that Fungi works off of. So if you want the module version, get this from GitHub. If you want the original file, it's just a regular JavaScript file. You can get it from Joseph's GitHub, and it's a great library. Works beautifully, very, very beautiful for Perlin noise. So that's the gist of that. So that's our terrain. I'm not going to really go through it because we already went through how this thing works. And I think one other thing I put in here, it's low poly Phong lighting shader. So we've got a new shader. That colors our terrains, and it kind of generates our pixel normals for us, so the terrain doesn't have normals. Actually, our terrain is incomplete because the original terrain that we generated, I'd also generated the normal directions for every point. This one doesn't have that. So if you need the terrain normals, just go back and fill in. It's probably another for loop, and then it's one of these get filled in. I think a normals are one of these values for the standard renderable VAO. At some point, like I said, I'll fill this in myself when I need it. But for now, I'm using the shader to calculate the normals for me. Oops, I just did something I shouldn't have. I don't know. What the hell is that? I don't know what that is. All right. So that's the terrain. So we have two test functions. One test is using what Thin Matrix did, and it was kind of really prototyping, and then I started having issues because I wanted to work in a certain way, and I could make it work how Thin Matrix did it, but I didn't like how it worked because to me it didn't make sense. And eventually, researching, I found some things. So I made test two. Test 2 is slightly different. Is using a slightly different approach. Same idea, less math. So I want to go through it, and I want to show you how I kind of came about it with the changes. Because you kind of have to sit and look at a bunch of numbers and kind of start seeing patterns in it. And I thought it was kind of important for you guys to kind of see that. So if we go on our test page, right? So we're almost getting there. We got our terrains, and we're building our terrain. We're giving our shader. We're pushing it to the scene. We got our camera, and here's how we're doing array. Array, say mouse segment. We pass in our X and Y from the mouse, which creates our array object, and then we call its prepare ABB, which also then returns our array object, and there we go. And then I call the static function, say, hey, I want to see the debug line of it. Boom. So like I said, right now I want the array data kind of separate from its visualization a little bit. So that's why they're treated as two separate items. So the array that we instance doesn't have debug like visual information. I have to call the array's static function to do that. And then we got our interim test. Like I said, we're gonna, like in the last couple of videos, I made a test function that's kind of messy, and then I give you a less messy version, or sometimes a more optimized version. And it looks like a long function. That's because we're doing a lot of checks. But a lot of these checks are kind of irrelevant. So everything that you see now pretty much generates this. Okay, so this is our terrain. This is everything I kind of just explained to you. Now, the first order of business, there's something I'm going to do that Thin Matrix did not do. I'm going to put a bounding box on our terrain. Right? So to me, that's like the first thing I'm going to do. I want a bounding box. And here's the reason why I'm doing this. So like I said, I'm building my bounding box. I'm passing it my terrain because that's my target. And I say update because I want to update its world values, its world bounding values. And then I want to create a visualization for it. The bounding box, I pass in my bounding box definition, and that's my shader that I want to use to render the bounding box. As you can see, everything's now broken down into separate little pieces. The ABB is our definition, terrain is our object that we're visualizing that actually exists in the world, and we're connecting them two together, and then we're connecting our bounding box visualization to the data. So this data is, like I said, there's the object, the data, and then our testing visualization. So if I click save, if I go back, refresh, now our terrain is surrounded by a bounding box that uses the max and min values. Now, one thing I did do, I probably forgot to mention, that in our terrain, I totally forgot about that, but I'm saving the max and min Y position. Oh yeah, that's another thing. That's right. I had a couple of things I forgot. So I'm tracking the min and max. So this way I know the bounds of my terrain chunk. Because remember, the definition of a bounding box is the smallest x, y, and z and the greatest x, y, and z. That creates the 2 points in our cube that we can define a 3D cube, basically. At the same time, I'm also saving the actual height of each point. So our terrain is a grid. It's a flat grid, and the Y position is different. But at the end of the day, it's still a grid. Oops, jumped in too early before I wanted to show you something. So you can kind of see the grid in the background. It's the same thing. It's just a grid, and as you can see, it's 5 quads across and 5 quads down. So if each quad is like 1 unit big, this is 5 units wide and 5 units long. So we know that this point is 0 and this point is 5. Like that's 0, 1, 2, 3, 4, 5. That's 5. Same thing. So that's our x position. So we know since we know the size of to create this terrain, we need to define its width and its height, basically. So we know we want, like I said, we want 5 across and 5 down. So that's 5 across. So we know the maximum x of our object is 5, because that's the total. That's the total amount of units we want it to extend. And the same thing with going this direction. This is the z-axis. So the z-axis, we know we want to go another 5 units, so that's max. So at this point, right here, of this cube, basically, that's 5 by 5. And down here is 0, 0. That's origin. So, but this point is 5 something 5. The y position is whatever the max y is, which is probably somewhere around here. This is where around the max y is, and I don't know, I'd probably say it's 1, 2, 3, I guess about 4 or 5 units tall. So it'd be like 5, 3, 5. So when we're creating terrain, we are also saving and calculating our bounding box information, our bounding information for this. Like I said, and another thing we're doing, so we're saving that, and we're saving for every point. We know what x, y, z. So for the grid, we know every point's x and z. We can very easily calculate it, and that's what we end up doing. So I'm not saving all the data that creates. I'm not saving all the vertex information that creates our grid. I'm only saving the y position, because we need that y position to calculate the point of intersection. Every other point on our terrain can be calculated based on the x and y, the x and z position. We can say, okay, here's the x, here's the z, and I know each point within it is like, one unit big. So if I know the first, it's hard to explain. I think thin matrix does a better explanation of this information. Like, to me, it makes vertical sense, but maybe if I start clicking things around, it probably makes sense when I start to visualize a lot of the things. So let's just say, like I said right now, I need to save the heights of every point. Instead of saving the x, y, z, I'm just saving y, because x and z can be calculated. Y cannot. So that's why we're saving y. And everything else stays the same. So now that we have a bounding box, right? One thing I wanted, now the idea of the binary search is that you have a huge array, a huge array, like from start to finish. You cut it in half, you test to see where it exists in the world, and then you find that bound and you cut it in half, right? So the array that we create is huge. We're going to create a very huge array. It's about 1,000 units long, because that's our drawing distance in our projection matrix. So instead of start doing that, since we were doing all these bounding box intersections, and in the event that this becomes like a texture, a terrain, a terrain chunk. So if we have like a bunch of terrains, and I want to click on it, each chunk is its own object. So the first order of business, if you have so many pieces, is find which piece that you actually connected to before you start doing all this ray math, marching stuff. So that's why I said, well, the first order of business is put a bounding box on it. So this way we can do bounding box testing. So the first order, like I said, the first order of business is, so if I had a bunch of these and I click the mouse, I do a search on all the terrain boxes that exist and find which one that gets an intersection through the array. And then you say which one's the closest to the camera, and that's the winner you pick. So for example, if I shoot a ray through here, here's our ray. And just like our bounding box video, you see the 2 points of intersection. So, see, the ray is huge. If I were to do it like normally, I would have to start down here, like somewhere down there, as the midpoint. There's no point. Why not just have a bounding box? Find the object we're dealing with, find its 2 points of intersection, and now instead of having this huge segment to calculate its position, I got that tiny little segment, because it's those 2 points of intersection on the bounding box. So that's a great way to optimize it. So this way we cut our searching by a lot. So once you have your segment, so there's a segment. That's our starting point. So that's the start, that's the end. We're gonna cut it in half. So that's our red point, the red point. Now that point of intersection that we're testing has an x, y, and z. So by using its x and z, we can calculate where on this grid that red dot is over. That red dot is over that quad in the grid, and I'll show you the math how you do it. But like I said, we know the x and z position. So let's say if I shoot the ray over here. So let's say the red line. Now the red line's over the terrain instead of being under. So let's say we say this is like 1 unit large, and the x here is 0.5, right? So since it's less than 1, we know it's in this unit. So let's say if I shut array over here, let's say it's 1.5, the x position. So we know, so if that's 0 and that's 1 and that's 2, that means x-wise it's somewhere in this column. And then based on the z position, you can tell where on this column this thing. So if that's like, let's say 1.5, 0.5. So we know 0.5 is 1 unit, is less than 1 unit. So you're in this quad. And once you know the starting point of the quad that you're working in, and then it's easy to just calculate and say, well, +1 to get the next point in the quad, and then you know how many total points there are. So if, there's 1, 2, 3, 4, 5, 6 points. So from here, I say, give me, because you save the points in order. So in the array, it's like this is point 1, that's point 2, 3, 4, 5, 6, 7, 8, 9, 10. So if that's number 1, I just say I want 6 more points ahead. So it's 1, 2, 3, 4, 5, 6. So you got the third point in the quad. Plus one more point, you're good. So once you determine the starting point of a quad in the grid, it's very quickly easy to discover the remaining 4 points of the quad. So that's the idea of finding the quad. And the next step, once you discover the quad, is that you need to actually determine which triangle, because you see how there's 2 triangles that create a quad. The next point is you need to determine which triangle the quad that you're kind of like this point is over. Is it over the first triangle? Like I call this the left triangle and call that the right triangle. Which triangle is that red dot actually over? Because once you could determine the quad and then further determine the triangle, then you can find the intersection point of the triangle. And I think we've done intersections before with triangles, but it's not the same thing. It's completely different. But like similar idea. All right. So let me explain further how this ray testing works. So now that we know, let's say, what triangle we're in, see how it is right now? There's the red point. Our midpoint is red, and then we have our things. So the idea is once we know which triangle we're in, we can then calculate using barometric coordinates to determine where this point is. And by using that array of heights, we can then interpolate exactly the height that this point is, because we know the height of this point, that point, that point, and that point, right? So we know those heights, but the height of that point, of where that actual intersection is happening, we don't know that height at all. So we have to calculate it. So that's why that's why I'm not saving x and y, because we need to calculate the x and y anyway, or x and z. Sorry. So we get the 4 points and the 3 points eventually, and then we interpolate the values. So this way we end up getting a whole new x, y, and z values that gets that exact point of intersection. Now we won't know the exact point of intersection yet because we're testing this point. So the idea of the binary search is that, like I said, we're taking the segment, we're cutting it in half, and here's the thing. What we need to know is the y position of this pixel on this grid. So once we know the y, we can say, well, okay, this is only like 1 unit, but this one is 2 units, right? So if we know that the y position is less than this thing is, we know that we have to do the search again. So it'll take this half of the segment and cut that in half. I don't think because I have the loop set up just to do once. Yeah, I just have to set up to do it once. If I do it twice, I think it ends up shrinking. The segment gets smaller. So if it does a second search, you see now the segment is no longer bound to the box. It's actually shrunken down. So like step 1, from here to here, and that was the midpoint. Second time, it took the segment and then cut it in half, and now it's testing. If we let the loop keep going, it'll take this line, cut it in half, and eventually by the third or fourth point, the fourth attempt, it would find the point of intersection. So we're just keep halving and halving until we get somewhere very close. And there's some limitations in it. I set up 20 tries, So there's two things. If we reach 20 tries, or the maximum distance between these two gray points is equal to or less than 0.3. If it equals that or less, we pretty much gotten as close as possible. So there's, like I said, there's two bounds to it. I'm testing based on tries and distances between the 2 points, because I kept testing it, and no matter what I did, the maximum tries I ever got was 7. Depending on the size of your terrain, you might have to require more tries, but the size of the terrain that I'm using, 7 tries is always the maximum. So, but I set up for 20. But like I said, the max try values that you use, which I'm not, I copied this into here to do that. But in the end, that's what you need to do. All right. So, like I said, now that's really the full algorithm. We just keep cutting this segment in half until we reach that point. And we have a bunch of garbage here that I'm seeing. Not garbage, it's really just information. All right. So yeah, we get our t values. We determine the delta, the length, because like I said, we're going to test the delta for the threshold. So the height threshold and the height delta. So the delta, I determined the length, and then I cut the length in half, and then that's our midpoint. That's the red dot. So we need these two values to calculate the midpoint. Then I take the midpoint and pass it into the mid t value. Basically, it's the mid t value. And then I want to get where on that array that t value exists, and that gives me the position. So I get the I position from array. And then we do our height, get height, position height test. So we pass in our I pose x, z, and then I'm passing in the debug object so I can output debug information or visualize the information. So now we're going to go into terrains. We're going to go into our height test. So this right here figures out our x and y position. Now, one of the first things we need to do is that we need to bring the x and z position of the mouse into local space for the terrain. Even if the terrain moved, we're going to move it into local space because it helps the math quite a bit. If we start, so I know what we say, we need to bring things into world space. This is one of the only instances that we kind of need to bring it into a different space to make the grid math work a lot easier. Because if you move things by weird increments, then the numbers aren't as even and they'll come out a little wonky. So if we bring our mouse position or I pose position into local space, we can then very easily recalculate the x and z positions very easily without any hassle. And you do that by just taking the position value of our terrain and subtracting it. So we have the mouse x and z, which I probably should put mx and mz so to make more sense. Actually, it's not the mouse really. That's actually the I position. So whatever. So x and z minus the world our world or our position for the terrain. So this way now everything's local z. To calculate the x and z of the first point in our quad is that we get the floor value of our x local divided by cell size. So like I said, the cell size is 1 unit big. And that's, and in this terrain, our cell size, I guess it's 2. I guess that's what I'm using. Is that what I'm using? Where's my terrain definition? Yeah, using the cell size is 2 units big. We have cells of 5. We have 5 cells. Maximum height is 3. We do a frequency of 3. These two are related to the Perlin noise. So that gets our X and Z position. So at this point, we know the X and Z of that point, the first point of the quad. So if I shot this, that's that point. If I'm shooting here, it's that point. It's always the first point in the quad. So once we get that position, TXTZ. I'm trying to think what's this? Now I'm confused by this part. I know there's two values. There's TXZ and there's UV. This is the confusing part. That's why I'm confused a little bit, because I did end up doing two different ways, and the UV. Is it the UV the quad? I guess so. So the quad, we're gonna put barycentric coordinates on it, and barycentric coordinates are essentially like UV values. They are one and the same. I think the only difference is that the UV values are flipped. I think UV values start here in the bottom corner, and one's over here. But since the grid is built from left to right, these UV barycentric coordinates are built this way. 0, 0 is the origin, like where origin basically is. So we're defining the quads. Oh, okay. All right. So yes, TX is the same thing as UV. They're the same values. They're the same equations. That's why I'm confused. Why they're all the same? Okay, because this is what I was using to do it how thin matrix does it, and then because of certain things I've read, this is the same concept but done differently. So these two are the same, but essentially we're trying to determine what are the coordinate, the UV coordinate of the I position. That's what we want to know. The coordinate that UV value. And to determine that UV value, like where in this quad that we exist, what is, like if I have the points here 0, 0 and the point over here 0, 0, 1, where in this quad is my X grid or my X local existing in? So we determine the TX and TZ or the UV value. These four are the same. This I'll explain a little later. And we're outputting information. And so yeah, so I just want to do recap. We're moving everything to local space. We're figuring out which quad, the X and Z of the first point of the quad that point of intersection is over or below. And then we start calculating the normal value of where that position is, or the UV value basically. Or in this instance, it's really the barycentric coordinates, but the same thing. They're the UV values. They're just flipped. So like this is a nice little example I put together, kind of just show you a little bit. This thing basically helps you visualize the 4 points that we're calculating. So remember I said that once you know the first point, you can calculate the rest. This is something I kind of came up with, is to kind of make something into a loop. I need to determine those other 4 points. And remember I said once you know the first point, all you have to do is calculate how much you need to go. So like here, I +1, then over here I gotta go by 6, and then +1 again. Now I can't remember how this pattern works. So a good thing I write notes down. Move pattern by X and Z, then by index of the quad points. So that's x, that's z, and then by cell divide plus 1. So suffice it to say, this like I totally forget how this works. This was like over a week ago. I've been slacking on making videos. I'm like done with intersections. Um, I'm sorry. It's also late. Yeah, it's like 12:30 in the morning. So basically, it's just a pattern to loop through, taking the starting point and then calculating the last 4 points of intersection. But yeah, that's the pattern: x, z, and index. So the third point is to get the y position. That's why I'm a little confused here. X, y, z, and then index to get quad points, which is the y. No. Crap. I hate when that happens. Full screen mode. Which is, I'll just say it. I should really write better notes. But this fourth point is to find the position here, because this is a flat array. So I need to find out exactly which point in this array it is. That's why I say index, because it's the index of this array that corresponds to the XZ position on the grid. So I end up using like I said, I use the X and Z grid values as the starting point, and then by using these values in an array, I change the starting point of the X, Y, Z to actually get the actual information for the point, which is a vec3, and I set that value. And then once I set that value, I add the position, which is, so this way, these are in local space, I add it to world space, so this way I can visualize it. That's the only reason. So all this is really just to see these 4 points, which is worthless. So I really shouldn't waste too much time explaining this part. But that's the visualization. So we don't need that anymore. We do not need to visualize that anymore, because we need to now go further and see where the Z is. So if I click save, I feel like something just closed I shouldn't have. What closed? That was the terrain file. How dare you? I'm messing up a lot. Sorry, guys. So click save. Now for refresh. Now next time I click, I'm going to get like new colors. But this time it's going to determine which triangle I'm in. See, if I'm on this side, it knows enough. So and it's the same order, RGB, right? RGB, red, green, blue. If I do it up here, red, green, blue. It's the order of definition. And in all honesty, the way you define each triangle is very important to the barycentric math. It's very important the way it's done, because it needs to be done in the right order, or if you're using thin matrix's barycentric functionality that he was using, then it doesn't matter. It kind of does matter the order. Let me change that, because I think I tried to change the order and it caused problems, and then I had to go back into his example and make sure everything is in the exact right order, and then his math starts working. And the new method I did, his order doesn't work. I need to change the order to work my way. It's really wacky. So now, let's see, what's the math here? Oh, that's a lot of code. Oh boy. So let's see, store the points. So we got a bunch of values. We're trying to calculate our x, y, z, and y. We're gonna store all our triangle points, and we're gonna store our barycentric coordinate points. This is pretty much, I think, a copy of this one, but it's a lot more. It's really the same, really. It should be the exact same math. Yeah, it's the exact same math, except instead of me throwing at everything in one big mess that's hard to visually see, this way you can kind of see the see a lot better. So you can see this is how we calculate x, this is how we calculate z, and this is how we calculate y. So since we're not visualizing, I'm not doing all this big glop. So we're determining the 3 points of our triangle. But we're determining both. Are we? No. Oh, never mind. Sorry. At this point, we're just calculating the 3 points. That's what this whole array does. It just calculates the 3 points. Okay. So here I save the 3 points. Here I save the barycentric coordinates, which I don't. Yeah, I do it here. And is there a change function? Yeah, there's a change function. And this change function has the barycentric coordinates. So here's 0, 0, 1, 1, 0, 0, 1. And I'm defining, like this defines the left triangle, and this defines the right triangle. So it's the barycentric coordinates and basically how to do the math to get everything in the right order to get the values. Now, there's a relationship that I didn't never realize about UV coordinates that thin matrix mentions, is that there's a relationship between x and y. In this case, we're saying z, but UV coordinates is a 2D thing, so it's x and y. There's a relationship between it. If you're going to do a diagonal and find any point on that diagonal line that's perfect, the relationship is that where is it? X equals 1 minus y. Whatever the x value is, if you say 1 minus that y value, they will equal, no matter anywhere on that diagonal line, even though it's broken. So for example, oh, what the hell? That diagonal line, if you can see it, that line, if I want any point on that line, whatever the x is, again, the y value will equal 1 minus y. It will be the exact reciprocal. If you're dealing with UV coordinates or barycentric coordinates, like I said, they're both one and the same, but they're just in different corners. They're just in different positions. But they are in that relationship. By knowing that relationship, if they are equal, then if x and y are equal based on that relationship equation, you know that any point that you point on is exactly on that line. I believe if x is less, is that how it works? If x is less? If x is less than y and z, we're dealing with this triangle. So if we say y 1 minus y, if x is less than that, it's this triangle. If it's greater than that, it's this triangle. You know, you have that equal position, so you can choose whatever you want. You can say if x is less than 1 minus y, it's that. And if it's equal to or greater than, is that. Or you can do it the other way around. We can say if it's less than or equal to, it's left. It's greater than, it's right. Either way, it doesn't matter. That center line, you can choose which triangle you want it to be part of. But overall, if it's less than, it's on the left. If it's greater than, it's the right side. So I never realized that relationship the 1 year I've been doing this, and I'm pretty happy that video explained it. Like I said, Thin Matrix is the man if you want to go and learn about game development. So by using that relationship, we know if we're doing the left, we're doing the right. And by doing that, if I'm going to the left, I'm going to start this array. I'm looping this array, this change array. That's what this loop is doing. I'm looping through this change array, and I'm going by every 3 points by here. So you see 3 points. So these 9 points on the array, or these 5 elements, 9 elements in an array, defines the left triangle. These 9 define the right triangle. So if it's less than, I just say I log. If it's greater than, then I say try star equals 9. So I equals try star, I is less than try star plus 9. And I plus equals. So I'm looping through this array. So if it's the left side, I'm going to say, instead of starting at 0, start at 9. And I want to loop 9 elements. So it loops till basically this point. If it's 0, so 0 to 9, it loops this much. So basically, I'm trying to be smart about creating a single loop that kind of partitions this array into two halves. That I can just by determining the start and end position, I can, do it that way. It's just being clever. It's clever algorithms that we're doing here. Just being clever. Because I use loops a lot, so. So once we know which triangle we're dealing with, like I said, this part is what determines it. Since once we know the tx and tz or the uv value, we know which one it is. Then we can use the Barycentric lambda function. He had one. Then I was having problems with it. Then I found one online, and it's almost identical, but a little bit more cleaned up. There's two versions to it. This is the original version of it. It uses x and y. I redid everything to use z because I need the z values, and it uses that multiplication trick. So instead of using division, it does the 1 over, and then it does multiplication. It's a more optimized version of what thin matrix uses, but it's essentially the same thing. The math is almost identical, or exactly identical. I don't remember. Like I said, he's the man. I'm just a poser. All right, I'm getting lost here. All right, so we're back here. Yeah, I'm losing. I had all the functions open. I hate that because then I forget which function I'm currently in. Sorry, guys. All right, so we can use the Barycentric values because we're saving the x and the x and z values. That's what these two values are. The first two values that we're saving is really the Barycentric values. That's why we're kind of saving it here. So it's change 0, change 1, and then our y value. Now the problem is I don't understand how this one works. Like you have to you pass in the Barycentric values as x and z, then which is only a value between 0 and 1. But as for the y position, you pass in a y, like the actual y value, which can have it can be anything beyond or before 0 and 1. And in the end, if you use the function, you do get your values. You absolutely do get your values, but you have to do all this calculations to you have to do all those calculations to get like a Barycentric like new values that then you can then apply the what this thing creates is like a weights, the x and y z weights or the UVW weights. To then you can apply it to your triangle to basically lerp the value, interpolate. It's the same thing what the GPU does when we define the triangle, and then in the fragment shader it gives you all the pixel points. That function plus all this is exactly what the GPU is doing for you. It's interpolating the values between the three points of a triangle, and then giving you each point exactly by the interpolation. So that's what all of this stuff is doing. It's interpolating those 3 points, finding the weights, then applying those weights on all the values to get you the actual x, y, z position in the world that pixel is on. Okay. So let's see if I can remember how. So now we have the triangle. Now here's BC is the values that we get back from the function. These are the weight values that we get back. And this is the same values that I'm calculating, right? See the BL. So okay, so let me back up a little bit. So we have the barycentric values, right? And now I'm doing a second one. But this one I'm using WUV. Right? Right up here. Now, the problem I was having with this barycentric function is that I did not understand at all why I put the x and z as barycentric values, like the UV coordinates, and then the y position gets to be any value. That for some reason that drove me nuts. I could not figure out why that's different. I thought we had to put, it just drove me nuts, and I don't understand. And like, if you don't do it that way, you will not get the values correctly, and you won't get the actual height that's interpolated. So you have to do it this way. Like I said, but the problem is I don't understand it. I don't get it. I can't really find much information on how it's done this way. I could have asked Thin Matrix, but I don't want to bug them. Now the thing is, when I was searching around the forums trying to figure something out, one post, I wish I saved the link, he mentioned that why do you need to search barycentric value, like why do you need that function when if you already know the UV values, like say we're already calculating the UV values, if you already know the UV values, the final weight values relationship is 1 minus U plus V. So if you add these two together, these final values together, and subtract it by 1, that will be W. Because essentially what we're doing down here with all this mess is to get the Y value. So all this mess essentially gets us that Y value, L3, lambda 3. So we're doing all of this stuff, and the relationship is kind of slightly different. It's 1 minus, it's all subtraction. But apparently the relationship the guy mentions that if you add these two together and subtract by 1, you get the L value. But I think you have to do it this way because the Y value that we're passing in, the B value here, is not barycentric. It's like it's different. It's the weird value. That's why I'm having problems with it. But if we already have, like he mentioned, that if you have the U and V values already, just add them together, and then subtract the sum of that value from 1, and that creates the W value. Because that's what that barycentric value is returning. It's returning lambda 1, 2, and 3. So that's U, V, W. So all this math is actually not needed. You actually don't need to do all this. I was like, when I read this, like, that can't be true. So when I start doing this, the output, lo and behold, it's true. The only thing I noticed is that the numbers were not in the right order. So once I start changing the order around of how I defined the triangles in a quad, the values start appearing in the right order as the function. So basically, I start reverse engineering that function but once I know that relationship and I'm outputting the information, I start seeing the values, but they're in the wrong order. And it's like, you know what? Since I knew the barycentric function needs things to be in the right order sometimes for the values to come out correctly, I start rearranging things, and to the point, just a little bit of trial and error, got them in the right order. So this way, the W relationship value matches up exactly to what the function outputs. So by using that little 1 minus the sum of UV, I was able to get that value without using that function at all, and without using all that math and division. It was insane. So, but at this point now it makes sense, because I have a UV value. I do a simple equation to get the W, and that is my weights for the thing. But that function, I can pass in the 2 points on no matter which triangle, and I get the BC value perfectly. The relationship that I have, that I'm just using the UVs to calculate the W, if I go to the second triangle, let me refresh. So this is what I'm calculating, and this is what I'm outputting. This is what the function outputs. So no matter which triangle, whatever triangle I'm using, it always gives me the right value. So all that math, even though it seems like a big waste of time, no matter what information I throw at it, it gives me exactly what I want. It gives me exactly what I want. The exact weight interpolation of that triangle. Once I did that, I was flabbergasted. I was like, damn, I thought this was going to work. It's not going to work. But here's the thing, just because by just seeing that it doesn't work doesn't mean it's not working. You really should always examine the data and really focus on the data. Give it a couple of minutes, because if you examine the data and give it some thought, you might see something. So like right here, like everything's in the right order. So like you see the first value, 309 and the other 75. It's the same value. It's the exact same value, but it's a negative. Okay, that makes no sense. It's the same value but negative. All right, okay. Then I look at the next value, 64. Okay, but I get 35. It's like okay, why? Okay, that looks a little weird. Well, I don't understand why that's different. I look over here, 66, 1, 33, 8. Now, I guess most people might look at this and it's like, man, the values are wrong. But that negative over here gave me a clue. Okay, why is that a clue? Because that is basically the opposite. It's the opposite. So the U value is the opposite. So if the function gives me this, but I'm calculating the UV myself, the UVW values, these are the ones that's being calculated using the shortcut. The U part is the opposite. This is positive, that's negative. If that's the case, you look at this, it's like, well, if that's the opposite, then how are these different from this one? When you look at the two, if you add them up, they equal 1. Then you look at the other numbers, you add these two together, they equal 1. It's like they're reciprocal of each other. They're opposites, basically. Where this one is like what's negative and positive called? Sign. The signs are opposite, but the values are opposite. And it's true with no matter which triangle I tested on and looked at the values. If I'm testing the second triangle, no matter what value it is the exact reciprocal of what the function gives me. Is the exact reciprocal. So you see there's BL and BR, and you notice that this value is exactly what the function gives me, because seeing the difference, I was able to calculate it. So like I said, W is just the opposite. I just said it a while ago, negative and positive. The signs it's the opposite sign. U and V are just reciprocals of it, so it's 1 minus. I get the opposite end of it, and there you go. So even though I have an if condition, and then like I said, I already know which triangle I'm working on. At this point, by using this relationship, I know which triangle I'm playing with. So if I'm playing with the right triangle, I basically just use WUV. If I'm using the left triangle, I use WV. And on top of that is another issue. even though UV, the order should be UVW, but to make this work, the order has to be WUV. It has to be this order. So it's kind of wacky, but it's kind of like when you're dealing with vec4s. Normally we say XYZW, but in all honesty, it's really WXYZ. So in this sense, we want to say UVW because the W is just an extra part of the UV, but in essence, the true order should be UWV. So to make this work, you have to use the true order because we're using 3 dimensions kind of with we're using barycentric coordinates. So there's 3 coordinates, so we need 3 values. So the order is WUV. Even though it's still 1, 0, because like this thing will give you whatever the right order no matter what for the most part. So if we're dealing with left, we use WV that we have, that we calculate at the very, very top. Right? We do 1 modulus and 1 division, and then we do an addition and a subtraction. Now, this can be simplified a little bit. Like I do the reciprocal of cell size and then do a multiplication. Because we do a lot of divisions. So we can get the reciprocal, the inverse of cell size, and replace these all with multiplications to speed up the processing. Because like I said, I keep reminding everybody, divisions are slower than multiplication. So if you're doing a lot of divisions with the same value, do the inverse, and then you can optimize a little bit. So yeah, so I can replace all this. 1 division, 2 multiplications, a whole heap of additions and subtractions. Like I said, with 2 moduluses, 2 multiplications, 1 addition, 1 subtraction. So overall, this is the more efficient way to do it. Even though, like I said, this is probably not the end all be all correct way of doing it. But if you're striving for efficiency, in this use case where we're dealing with a grid and we can determine which triangle of the quad that we're determining, this method would be the most optimized way because you're dealing with less math operations to end up calculating your positions. Because in the end of the day, this function could be replaced with something simpler, and then you're stuck still doing all this multiplication addition anyway. Like I said, in this use case, it's probably the most efficient way. And if the guy is right that that's the relationship, I wish I remember his name in the forum. It works. Like I even though there's an if statement that I have to add, which I have to change the values between which triangle I'm dealing with. It's still true. The relationship is true. It's just it's inverted. But like I said, for this use case, you can do it either way. You can use the barycentric functions and not worry about it, or you can use my funky way, which is simpler mathematically, but it's more efficient if you're doing a whole mess of intersections. And mind you, we're doing a binary search, so we need to call this function probably up to 7 times to find the point of intersection on our terrain. So like I said, the simple relationship of W is better because we end up, like I said, all this math times 7. So that's how much instructions we're passing to the CPU to do the math for us. So if we can cut this back down a little bit, it'll help speed up our intersection testing. Like I said, we have to test multiple times. And that is the gist of it. So if I go to test 2, here you can see I start optimizing it. Cell size inverse, I actually do it in the constructor. Like if this terrain exists, once it's created, I save that value. So in the math part of it, I never have to worry about it. So I can just go straight into multiplication. And then I think this still has some visualization. So let's see. So this is the second function. So if I go here, I'm going to start using the new the function that's more optimized, that doesn't use the barycentric functions, and it should function just fine. And this one actually eventually shows you the point in which that we find. So we find x and y in the x to z value, and then by that barycentric thing, we calculate its height that's interpolated from the 3 points of the triangle. So as you can see, this is the point on the grid or on the terrain that this point is. So we compare that y with that y, right? So if that y value of our I position is greater than the y that's on the terrain, we're going to use the second half of the segment. So second half of the segment. So if I were to just say max tries, then we just keep going until we end up cutting the line in half. Let's see what else. So yeah, we're doing a loop, and if I say loop equals 3, I know I did like the numbers differently in this time around. I did some small changes because I found the original change thing complicated because I was mixing the height index with the UV coordinates or the barycentric coordinates, the zero, this stuff. I found it to be confusing. Like that's why I said when I saw it for the first time again in over a week, I was like, oh man, this is confusing. In the second version of it, I split it into two separate arrays. So that's why the values are different. Even though it's the same idea and the variables are different, it's the same idea as the first one I'm doing. Like I said, this is more optimized and more cleaned up. Less information, and like I said, it's easier to. So it's the height offset for the quad points. This is the left and right triangle, and you can very easily see what the barycentric coordinates I've supplied. And like I said, they have to be the order of like this is the exact order that needs to work for this entire algorithm to work. So this way the UWV values appear in the right order, and then we can determine the left and right triangle of the quad. So like I said, this is very important. This is very important. This is the order it needs to exist in. Yeah. So, and I'm caching the vert. Don't remember why I'm caching it. Oh, okay, that's why I'm caching it. So the reason why I'm caching, like it's the same the previous one. I call it try, but this time I'm calling it cache. I'm caching it because I got to take those 3 points in the triangle to help me calculate the x, y, and z. Now here's the thing: I'm calculating x, y, and z. I don't need to calculate the x and z. I really don't. The x and z values are the x and z values that I pass in. I don't need to do the extra math to get the x and z value. I really don't. Why am I doing this? I'm doing this to prove to myself that the math I'm doing is correct. Because if I get if after all said and done, all these equations, these math values, if they end up calculating the exact same value, then I know the math is sound. So in the final version, there's one more optimized version of it. I cut out all the fat, but like this is like the second prototype. which then leads into the final version of this function. At this point, like I said, we don't need all this. This is to help me visualize it too. So at the end of the day, this is the only point that counts at the very end, because we want the interpolated height, because the x and z positions are the exact same thing that we passed into the function to begin with. They are the exact same positions. So, but like I said, x and z is only here to prove that the WUV relationship that we're calculating is true. If it create, because like I said, I was having a lot of problems and x and z were not matching. So doing this made sure that x and z matches and all the math is sound and everything works. And at the very end, when you're all said and done, you take the y value that you calculated and you add it to the position of our terrain, because it's an object. So this y value in the end of the day, at the end of this function, is in local space. So we need to add the position y to bring it back into world space, because in the actual function in here, this h point is the actual height in world space. So h delta, I actually test to see the height difference. So the height difference. So if the height between the I position and the h point that we found is less than or equal to this, then we're good. We found the actual intersection point. So that's the first thing. We're going to check to see if the height is within it. The next thing is we're going to check our exit strategy. Our exit strategy, like I said, is the delta. If the delta is less than the min delta, where's min delta? T. Oh, that's T min delta. If the distance between the 2 points is less than that, remember this is right here, this is the delta, the T delta. If this value right here that we calculate is less than or equal to this, we're done. That means the two gray points, these 2 gray points are too close together. If we did not find an intersection point, by the time that these 2 points are really close together, then we're done, because that's the minimum range we can do, because when you're dealing with like large numbers like that, you kind of have like this infinity near zero, so you kind of want to stop at a certain point. So once we reach that point, it's like we're done. It's like I give up, you know. So if it's less than that value, or our I in our loop is greater than or equal our max tries, we missed. The intersection, there's no intersection. We can find an intersection. So those are our exit strategy to end this algorithm. The next thing is, if the h point that we discovered is it greater than y, then we kind of set the t max to be the min. Else, t min is our t min is the t mid that we calculate. So at this point we're figuring out for the next loop. So this is the first try. So like I said, that's why we do I have a value? I say try was 1. So I want to find out which. So here's the point that we're testing. We're testing these 2 points, and in the end, this is down here. So min stays the same. This max value now takes the midpoint as the max value. So this becomes max, the new max, and this is min. So next time we loop, we cut this in half and we test the midpoint of that segment. And that is the end. So with max tries, and we're using the test 2, if I were to refresh and shoot a point, it now finds the point intersection. As you can see, the black dot and the red dot, it's probably hard to tell, depending, they essentially exist in almost the exact same space. almost the exact same space. They're like overlapping each other. So that means, and you can see the two, it's kind of hard to see the two gray points. Oh, we don't want to go too far. Okay, I got too. I think I can't really get there. I can't zoom in with that fine of a detail. But as you can see, the red and black are almost touching each other. There's that little delta difference. And that's our range. It's really, really small. When you're zoomed out, they're like essentially all on top of each other. And we got hit on 7. And that's what this little, like I have the output telling me. Like I said, the maximum I get is usually 7. So if I click again, hit on 7, that's the ray point. It's on that triangle. That one got hit on 6. Sometimes if I hit it straight up, hit on 6. That one's a hit on 4. So yeah, like I just kept shooting. That's a hit on 5. Just kept hitting. I think 4 is the minimum. Like I need to test at least 4 times, but maximum of 7. Oh, this one's 1. This is that only took 1 loop. Yeah, that one, because that was the perfect midsection. That was perfect. Ah, look at that, beautiful. On the first try. And if I were to shoot over here, no intersection. Oh, so it knows not the intersection. And it knows there's no intersection because there's no because it didn't hit the bounding box intersection. So there's no bounding box intersection. So it knows, like, there's no even point even searching. If it's not even touching the bounding box, don't even waste all that time doing the math. So that's why I kind of, like I said, the first order of business is to set up a bounding box, because the bounding box is very simple to calculate, and it, like I said, it helps us limit the size and distance of our tests. I think, like, also one last test is that you want to zap right across. See, it didn't touch the terrain, but it is within the box. And it took 9 tries to determine that it's a miss. So that's like the final test. Like, you're in the bounding box. You're parallel to it. But yeah, it does. I guess it did a bunch of tests. So that's the point of intersection. You know, everything just, and there's, I don't know. In the end, the red dot's up there, black dot's here. There's no way to get closer to it. So I guess what ended up stopping it is the distance between the gray lines. Once that the segments of the dividing segments get too small, I stop. Like I said, right here, the T delta. This once those those 2 gray points are too close together, I stop. So that's why I probably at test 9 is like, nope, sorry. There's definitely no intersection. Yeah, and that is it, really. Look at that. And that's the whole point of this is how you intersect terrains. Now, the reason why you have to do this is because because of the shape of the terrain. There's no easy way to determine it. It's very there's other methods. Like another idea is that you go through each triangle in your mesh and you do a triangle intersection test. That will take a long time. The bigger the mesh, the longer it's going to take to find. And you have to search everything, because you might find there could be 2 points of intersection. Not on a terrain. A terrain depends if there's like a hill valley. You know, if there's a hill, or like kind of I got rid of that. Yeah, like this. If you have something like this, there's more points of intersection. And if you're going to test all the triangles, you have to test literally every single triangle and then find the triangle that's closest to origin, and that is the correct point of intersection. But yeah, that's kind of a that's a lot of processing. Yeah, the greater the terrain or the greater the mesh, the longer it's going to take. So by doing this kind of ray marching approach, you're and especially we're dealing with the grid, it's easy to calculate the X and Z positions, and then you have to go through you got to go through a loop to kind of get the Y position. That's really the big magic behind it, the secret sauce. It's that dividing the line and then testing where that point is over the terrain, and then finding that point on the terrain that it's over, and then comparing the Y position. This one, this is about an hour long, or an hour and a half long, I'm not sure. It's very long. My throat already hurts. And that is, like I said, I keep saying this, that is line intersections with terrains. And you got all that visualization to help debug these things if you want to figure it out. And now we're going to have a little bit of fun. There's not going to be no more intersections. So I just want to show off the new terrain function. So let's see. So yeah, we just give it its XYZ, its spec, and then we set its position based on whatever our N is. If I click refresh, there's our one piece of terrain. Let's see, make it two pieces. Refresh. Ooh, now we get this is four pieces in actuality. There's 1, 2, 3, 4. I say two, but it's like 2 by 2. Let's see. I think, is it 10? Maybe it's probably 8. Create 8. Click save. Refresh. Oh, there we go. All right, there we got some terrain going here now. There you go. And these are chunks of terrain. So if you put a bounding box on each one and you do a search on that, like I said, this is seen as an array, so I'm just throwing them all in there. And you just search the array bounding boxes, and then that means you'll end up finding the exact chunk of terrain that you're testing intersections with, which is not working because I don't have it in existence. So yeah, like if you did that, you did a search, found the right bounding box, and then you just stay within that terrain chunk to actually determine the point of intersection. So this way, you're not dealing with all of this. You're only dealing with a subsection of your overall terrain. And terrain chunks are very important when you want to create infinite terrain. So the idea is that, since you can create grid terrains, you just, as you travel in the X or Z position, you just keep adding on as you travel, and then you get rid of the previous points. So a long time ago, when we created terrains, we created this one piece that existed in the middle of origin. Now it's actually created at the corner of origin, and you can position it anywhere based on your thing. And you can change its frequency and everything else. So if I want to make it taller, I can say, let's make it 5 or refresh. Now our terrain is a lot more hilly. Now it's starting to look like an island. Like this, you can consider the grid to be water, and that's a little lake over there. Frequency and seed. You can change the frequency. You can say, well, this is like information for pollen noise. We did a video about pollen noise, so frequency is like how often the switch. 13 made it very smooth. This one, make it like you can always play around with the numbers, and you end up getting different results. So let's see, 13. That's 3. Let's try something like 20. What's the frequency of 20? Refresh. It's similar to what the 13 is, but a lot bigger and smoother. Technically, what frequency really is level of detail. So the higher the frequency, the more zoomed in you are. So if you're building a world and you need a level of detail. You might start off at, like, let's say a frequency of 5. You know, from space or whatever, this is what the terrain looks like, essentially. You know, and then see this water in that lake spot. Like, we're in space, so if as I'm flying toward the terrain, you can then recreate the terrain with a higher frequency. So let's move on to like 9. That water and that lake should be there, but now it's smoother. We're getting closer. See, it's still there, but now everything got smoother. Now we're more zoomed in. And then we go to 13. Oop, don't want that. Click save, refresh. Again, now we're there, but now we're even more zoomed in into that section. So yeah, so at some point down the line, I want to do a level of detail video dealing with the terrains. I want to do like a big, huge series related to terrains, because there's a lot of things you can do to terrains. There's like these biodome type of things where you can where you combine 3 frequencies of permanent noise, and you can create these very more realistic hills. Some are jaggedy, some are smooth. It's like a mix and mash of it. Like this one, we're dealing only with 1 frequency. The other one, the more complicated way of doing it is like 3 frequencies, and each one is a power of 2. So the first frequency is like 13, and then the next frequency is like, I don't know. I forgot. I actually played around with this before, and I can't remember how. But I know it's like a power of something. I had to find the JavaScript code I wrote like months ago. But the idea is that you have these 3 frequency values, and then you blend them together, like you add them up, and then you apply it into permanent noise, and you get this nice mix of like jaggedy and smooth areas. Yeah, and you get this nice mix of smooth areas. And by using these values, you can also determine color, like textures. Like if certain parts of the hills are really high, you can paint it white, so it's kind of like snow. If things are really below the line, like let's say if any white position that's under like 0, you can paint it blue, like for water. And then anything that's kind of in between, you can paint it green or brown, you know, depending on certain values. So this way so instead of having a single color, you can actually have everything kind of biodomed out a little bit. So, and then of course there's level of detail, like I just showed you. By changing the frequency, this section we saw from really high up, like a high detail, and then as we got the frequency value got higher, we kept zooming in. So maybe I would like to do like an infinite terrain thing, where we kind of just keep going forward or backwards, and we just keep adding on and removing terrain chunks. I want to do something like that. Level of detail, so we can zoom out really far into space and then zoom in, and as we zooming in, we swap in chunks. That's using like I think something called an octree. So if we're zooming into a certain section, we replace that section with a more zoomed in version of it, and as we get further closer to it, the other section that we're over, we then divide that up and then make new chunks. Look up octrees. It's a very interesting algorithm. That's how you would handle level of detail. That's essentially the idea behind it. So this way you kind of divide your world up into like coordinates, like giant massive grids, and depending what grid you're in and the how far you are from the ground zero is the level of detail that you're currently being displayed. So you kind of create the terrain chunks, and then it's somewhere in between a frame, you kind of just swap it. where it looks seamless. Like that's the tricky part, is finding at what point is it seamless to kind of swap uh, the high quality version, because the more zoomed out you are, the low quality you are, and the more zoomed in you are, the more high quality. Like it's like, because you can see it's more detailed, you can see things. It's more smooth and less jaggedy because we're more zoomed in into the world. So that's like the level of detail type of thing I'm talking about. So that's the only trick, is that balance between. I haven't really done it like that's I've been reading a lot about that, but I'm not going to deal with that for a while. And I really want to deal with water too. So once whenever I get into terrains, I want to be like raycasting, where I'm going to do like this long stretch of videos about terrains, like all the different things you can do, and like the end of it, I want to basically create like a planet, and you're in space, and you can fly into the planet. That would be kind of like the end, the milestone, that the end point of that series is really start making these chunks, start dealing with biodomes, start making infinite terrains, and then eventually start doing a level of detail. And then maybe build a sphere world, and then divide that up into grid sections, and then as you zoom in, you create level of detail. So I don't know when I'm going to do that, because I want to finish armatures first. I want to do animations for armatures, and I want to do voxels. I want to do like a level editor with voxels. And then I think once I'm done with voxels, I'll probably come back to terrains and really do terrains, because then we can build worlds with it. Like I said, the endpoint will be to create a planet that we can be in space and then fly into it. A lot of cool games do that. It'll be great to really experiment with that and really get that working just right. I think a lot of people will find that fun to do. Not really a lot of tutorials on how to do it. Not necessarily in OpenGL or WebGL. Definitely quite a bit in Unity. If you're really interested, you'll find a lot of examples, I think, in Unity how to do it. But the thing is, it shows you everything that Unity gives it for you. Where like what I'm doing, what some other people are doing, you're building a game engine, so you kind of have to deal with more the nitty gritty things of building this stuff, more than nitty gritties. But it's fun because you're building it yourself. You're controlling it. You know every aspect of what you're building. That's always been the problem I found with Unity, is that it's a great tool. It's great if you're getting started. But at the end of the day, AAA companies, they always end up building their own engine, or they use Unreal, but then they modify the hell out of it. So yeah, that's really how like AAA they end up doing it. Either they make their own game engine, or they mod the hell out of Unreal. And Unity is not moddable, so you have no control. You're stuck with what Unity gives you, and what little expansion you can do just by adding scripts to it. But you can't change the overall structure of the Unity game engine. Now, there's a lot of open source game engines out there, though. There's Blender that you can use. Lumberjack that Amazon has. Surprisingly, Amazon.com has a gaming engine. There's a free one, I forget what it's called. It's Godot game engine. Yes, Godot. Definitely something worth checking out if you want a free open source game engine that's kind of like Unity, and it's kind of like I think it's written in C++. So it's kind of Unity like, Unreal like. It's kind of like I guess a nice blend. So if you don't want if you don't want to build your own game engine and you just want something good to start with, I highly suggest Godot. But you have to know C++. And it's kind of like Unity, where it's multi-platform, so you can hopefully compile it to work on like I think you can compile it to work on mobile. I'm not sure. Don't quote me on that. But yeah, like if you're enjoying what you're doing, building an engine, go for it. But like at the end of the day, if you want something that has a lot of features already, but you want the ability to go in and tinker with it, and you don't have to pay licensing fees, Godot is probably your best bet for game engines. Other than probably Blender. maybe Lumberjack, but I have no. But if you like I said, if you want to stick with open source and with a really nice community of people, GoDad's probably one of your best bets right now for game development. Like I say, if you don't want to deal with the big boys, like if you don't want to deal with Unity, Unreal, because any games you make with those two engines, you have to pay royalties. Godot, you don't have to. If it's open source, it's free. You should be able to do whatever you want. It says right here, completely free and open source under very permissive MIT license. And like I said, it's open source, so you can modify it. And it comes with an editor too. So like I said, it's like Unreal and it's like Unity. You have an editor. It has all the tools you need to build a game. So I don't know why I'm hyping up this. Like I'm trying to teach you to build a game engine. I'm telling you, okay, go use this instead. Again, if you want to build something now, but you want to be able to tinker with it, give this guy a try. I would suggest it. I might end up doing that at some point if I just want to build something and I don't want to build the entire engine, which is not true because I want to build my engine for the most part. I just really do. I just want to be able to say I completed an engine. Here it is. It does X, Y, and Z. Okay, now I'm going to use Godot. That might end up being the situation, but hopefully I'll learn enough to the point. The whole point of the series, I guess, for me, is that I want to build a game engine. You guys will probably want to build a game engine. We're going to build all the nitty-gritties and then start dealing with a lot of high-level things. Like we're starting to deal with terrains and maybe a level of detail. That stuff is those things are theories that are interchangeable depending on what engine you're in. Those things are very high level. They're not they're not like metal. I forget what the term or the phrase is. It's not like right there, like deep into the game engine. That stuff is kind of like you use game engines to build that stuff. Like Godot would have all that raycasting stuff. You wouldn't need to do that. That means, but for us, we're building game engine. We have to deal with the nitty gritties. That's why for the last 5 or 6 videos, we're dealing with all these raycasting things. So, but it's, I guess, and at the end of the day, if you can build your own game engine, you can then go to Godot, you can go to Unreal, you look at the source code, you will have an understanding of what's going on, and you can start tinkering with it. That's really the real important thing. Like, if you can build your own, you can then join these guys and then build a game using their engine and add on to it. Join the community and add to it. Build chunks of code that other people come in and learn from, and things like that. I'm a big open source advocate. So, like, to me, I would rather go here than the other engines that are not open source. And you have Source Engine from Valve, but I heard that's a mess. I've read that's a big mess that people really would rather not deal with Source Engine or Source Engine 2. But it's another option if you want to, game engine wise. And my throat is going to hell right now. So yeah, this is episode 50. This was going to be the end of the intersection video, but like I said, it's been over a week since I've actually finished doing this. I'm going to make one more video because I remember in video, I think 23, we created picking and we used frame buffers. So in the next video, I want to use intersections to do gadgets. So we had that like translation gadget. And we use ray intersections. I already did that, and it's going to be a better version of it. So this way, the next one we're going to deal with, it's kind of how to use ray intersections to create a gadget, and then this gadget can be attached to a cube. And while we move this gadget, it will move the cube right along it on the axis. And this one's going to have I think more functionality where you can do X, Y, Z. And it can do planes. You can do the X, Y plane, the Z, X plane, whatever. It's the 3 planes of space. So you can the gadget I already put together. It's really kind of really neat. It uses intersections, but differently. So you actually get to learn something different, because instead, I don't want to go too much in detail. It's, I guess, a bonus when it comes to intersection, because it's intersecting without intersecting. Now let that rack into your head a little bit. I'm testing intersections without actually intersecting. That was the fun thing, and surprisingly, I managed to do that completely on my own without the help of anyone, except for one equation. I did have to find a specific equation to determine something that I need, which I kind of already had. I had one that was from point to lines. What I needed was an equation in relationship between two lines. So once I found that function that gives me the value between the relationship, the intersection without actually intersecting worked beautifully. So the next video is going to be the bonus video, the final video of ray intersections. And I probably, very long video. Probably spent too much of it talking about other things. But yeah, hope you're having fun. This is great. This one video we kind of talked about, finished into ray intersection. We did terrain chunks. Talked a little bit about level of detail, how to use Perl and noise, basically kind of build that level of detail if you want to start experimenting. So yeah, this is great. Oh man, my throat is killing me. So I'm gonna end this now, and see you guys in the next video. I hope if you please like and subscribe. Blah blah blah. Have any questions? Ask away. And I totally forgot, I was going to name the two people that the two extra people, not just recently but like a while ago, gave me some Patreon money. I don't want to log in right now because I don't want you guys to see my account information. I was going to log in and then have the names ready, but I totally forgot because it's really late. But you guys know who you are. The two additional guys that they gave me cash on Patreon, I really want to say thank you very, very much. I hope you're enjoying. I hope you guys are enjoying the videos. I know this whole ray intersection video is because of one of you guys asked the question, that they asked for help on ray intersections, and I hope whatever schoolwork you were doing that you needed understanding of this worked out great. So I hope you got an A, at least an A minus. But at the end of the day, I don't care. I don't care if you got a D, as long as you understand this and you have fun. That's all that matters. If you're doing this to make games, you're doing it because you love it. And if you love something, you'll get better at it sooner than later. So again, like and subscribe. You don't have to give me Patreon, but anyone who does, I'm very, very thankful of it. Thank you very much. See you guys at the next lesson.